In 1808, John Dalton, a self-taught Quaker scientist from Cumberland, England, published a new system of chemical philosophy, a work that would transform chemistry from a collection of observations into a quantitative science. Dalton proposed that all matter is composed of tiny, indivisible particles called atoms, each element having its own unique type. This revolutionary idea, built on precise measurements of combining ratios, laid the foundation for modern chemistry and atomic physics. Niels Henrik David Bohr was a Danish physicist who made foundational contributions to understanding atomic structure and quantum theory. He earned his PhD from Copenhagen in 1911, worked with J.J. Thomson and Ernest Rutherford. Inspired by Rutherford, Bohr developed his quantum theory of the hydrogen atom in 1913. By the early 1900s, scientists knew that heated elements emit light only at specific wavelengths. Johann Balmer discovered the visible hydrogen lines follow a pattern. Rydberg generalized this formula, yet no one could explain why discrete lines existed. Bohr provided the answer. Bohr proposed three revolutionary postulates. First, electrons orbit the nucleus in stable stationary states without radiating. Second, angular momentum is quantized as mvr equals nh over 2 pi. Third, electrons transition by absorbing or emitting photons with energy delta E equals hf. Bohr derived energy levels for hydrogen. En equals negative 13.6 over n squared electron volts. The ground state is negative 13.6 electron volts. The first excited state is negative 3.4. Higher states converge toward zero. This matched experiment with astonishing precision. Bohr calculated the radii of electron orbits. The Bohr radius is 0.529 times 10 to the negative 10 meters. Orbits scale as Rn equals n squared times a zero. The n equals 2 orbit is 4 times larger than the ground state. Orbits grow quadratically with n. Bohr's model explains the hydrogen spectral series. The Lyman series is ultraviolet. The Balmer series is visible with H-alpha at 656 nanometers, H-beta at 486, H-gamma at 434, and H-delta at 410 nanometers. The Paschen series is infrared. Each series converges to a limit. Bohr's model provided the foundation for spectroscopy. In emission spectroscopy, excited atoms emit bright spectral lines. In absorption spectroscopy, cool gas absorbs specific wavelengths from white light. Each element has a unique spectral fingerprint used in astronomy and forensics. Despite its success, Bohr's model had limitations. It could not predict spectra of multi-electron atoms. It failed to explain line intensities and fine structure. It violated Heisenberg's uncertainty principle. It was superseded by the Schrödinger equation in 1926. But it remains a crucial conceptual bridge. The Frank-Hertz experiment in 1914 confirmed Bohr's model directly. Electrons lost energy to mercury atoms only in discrete amounts of 4.9 electron volts. This proved atomic energy levels are quantized. Frank and Hertz won the Nobel Prize in 1925. Quiz question 1. According to Bohr's second postulate, what condition determines which electron orbits are allowed? Option A, kinetic energy equals potential energy. Option B, angular momentum must be an integer multiple of h over 2 pi. Option C, the orbit radius must be 0.529 angstroms. Option D, electron speed equals light speed. Quiz question 2. What is the energy of the n equals 3 level in hydrogen? Option A, negative 4.53 electron volts. Option B, negative 1.51 electron volts. Option C, negative 6.80 electron volts. Option D, negative 0.85 electron volts. Quiz question 3. The Balmer series corresponds to transitions falling to which energy level? Option A, n equals 1 Lyman. Option B, n equals 2. Option C, n equals 3 Paschen. Option D, n equals 4. Quiz question 4. What is the radius of the n equals 2 orbit in hydrogen? Option A, 0.529 angstroms. Option B, 1.06 angstroms. Option C, 2.12 angstroms. Option D, 4.76 angstroms. Quiz question 5. The Franck-Hertz experiment provided direct evidence for which aspect of Bohr's model? Option A, existence of the nucleus. Option B, quantization of energy levels. Option C, wave nature of electrons. Option D, elliptical orbits. Problem 1. Calculate the energy and wavelength of the photon emitted when a hydrogen atom transitions from n equals 4 to n equals 2, a Balmer series transition. Step 1. Calculate the energy at n equals 4. E4 equals negative 13.6 divided by 4 squared, which is negative 13.6 divided by 16, giving negative 0.85 electron volts. Step 2. Calculate the energy at n equals 2. E2 equals negative 13.6 divided by 2 squared, which is negative 13.6 divided by 4, giving negative 3.40 electron volts. Step 3. Find the energy difference. Delta E equals E4 minus E2, which is negative 0.85 minus negative 3.40, giving 2.55 electron volts. Step 4. Calculate the wavelength using lambda equals hc over delta E, using hc equals 1240 electron volt nanometers. Lambda equals 1240 divided by 2.55, giving 486 nanometers. Step 5. This is the H-beta line, blue-green visible light. The answer is an energy difference of 2.55 electron volts and a wavelength of 486 nanometers. Problem 2. Calculate the ionization energy of a hydrogen atom from its first excited state, n equals 2. Ionization means removing the electron completely to n equals infinity. Step 1. Recall Bohr's energy formula. En equals negative 13.6 over n squared electron volts. Step 2. Calculate the energy at n equals 2. E2 equals negative 13.6 divided by 2 squared, which is negative 13.6 divided by 4, giving negative 3.40 electron volts. Step 3. At n equals infinity, the electron is completely removed, so the energy is 0. Step 4. The ionization energy is delta E equals E infinity minus E2, which is 0 minus negative 3.40, giving 3.40 electron volts. Step 5. The ionization energy from n equals 2 is 3.40 electron volts. This is much smaller than the ground state ionization energy of 13.6 electron volts. The answer is 3.40 electron volts. Problem 3. For hydrogen in the n equals 3 state, calculate the angular momentum of the electron. Step 1. Bohr's quantization condition. L equals nh bar equals nh over 2 pi. Step 2. H bar equals h over 2 pi equals 1.055 times 10 to the negative 34 joule seconds. Step 3. For n equals 3, L equals 3 times 1.055 times 10 to the negative 34. Step 4. L equals 3.16 times 10 to the negative 34 joule seconds. Step 5. Angular momentum is quantized in units of h bar. The answer is 3.16 times 10 to the negative 34 joule seconds. Problem 4. Using the Rydberg formula, Calculate the wavelength of the first Lyman series line from n equals 2 to n equals 1. Step 1. 1 over lambda equals RH times 1 over n1 squared minus 1 over n2 squared. For Lyman, n1 equals 1, n2 equals 2. Step 2. Substitute. 1 over lambda equals 1.097 times 10 to the 7th times 0.75. Step 3. 1 over lambda equals 8.228 times 10 to the 6th per meter. Step 4. Lambda equals 121.6 nanometers. Step 5. This is Lyman alpha in the ultraviolet. The answer is 121.6 nanometers. Problem 5. Calculate the orbital speed of the electron in the ground state of hydrogen, n equals 1. Step 1. V1 equals E squared over 2 epsilon 0 h. Step 2. Substitute constants. E is 1.60 times 10 to the negative 19. Epsilon 0 is 8.85 times 10 to the negative 12. H is 6.626 times 10 to the negative 34. Step 3. E squared equals 2.56 times 10 to the negative 38. Step 4. V1 equals 2.18 times 10 to the 6 meters per second. Step 5. This speed is approximately c over 137, the fine structure constant. The answer is 2.18 times 10 to the 6 meters per second. Let us review key concepts. Bohr's three postulates: stationary states, quantized angular momentum, photon transitions. Energy levels: En equals negative 13.6 over n squared. The Bohr radius. Spectral series: Lyman, Balmer, Paschen. The Fraunhofer's experiment confirmed quantization. Niels Bohr's model transformed physics forever. It bridged classical and quantum worlds. It led to quantum mechanics through Heisenberg, Schrödinger, and Dirac. Modern applications include lasers, atomic clocks, and spectroscopy.